And the following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, today we're going to go on and cover section 11.4. But before we do, there was one question emailed to me, so we'll take a look at that. This is from section 11.3, problem number 16. It says the charge remaining in a battery decreases as the battery discharges. The charge C in coulombs, I'm not sure how you say that, after T days is given by the formula C equals 3 times 10 to the negative 4 power times 0.7 to the t power. Find the charge after 9 days. Round your answer to 9 decimal places. Okay, so after 9 days, t would be 9. So we're going to take c equals 3 times 10 to the negative 4 power times 0.7 to the 9th power and see what we get. So parentheses 3 times 10 raised to the negative 4 power, close parentheses, parentheses 0.7, close parentheses raised to the 9th power. And I get 0.0000121006. And by golly, that is 9 decimal places. So there's the answer. Or you could write it in scientific notation, 1.2106 times 10 to the 1, 2, 3, 4, 5, negative 5th power. So either this answer or that answer. Any questions on that? All right, well then we'll continue on to section 11.4. So let's say.
Sorry, Mr. Mayo, I actually have a question about that.
Yeah, the one we just did? Okay.
Yeah,
sure.
Only because my calculator, when I put it in, it gives me the 1.2106 as my answer.
Okay, does it say this 1.2106 e negative 5?
Yes.
Okay, so that's scientific notation. That E stands for 10 to the.
Okay, so then if I'm going to move if I get that answer and I go to move my decimal place 9 over.
Well, you wouldn't.
Will I easily recognize that if there's a bunch of zeros in front of it, kind of a thing, or just look for that E symbol and move the
just look for that E symbol
first?
Yeah,
okay.
And there's a way to set your calculator so that it doesn't automatically go into scientific notation. What calculator do you have?
I actually have a TI 83 plus. So mine's a little for the next class. Mine was for the next one. So.
Okay. Hang on just a second. Okay, so continuing on, we'll take a look at section 11.4. Now, let's see. Are we back to the whiteboard? Yes? Somebody?
Yeah.
Thank you. Thank you. Okay. 2 to the 3rd power equals 8. 2 to the 4th power equals 16. So my question is 2 to what power equals, let's say, 11? Okay. Well, looking at 2 to the 3rd is 8 and 2 to the 4th is 16, x in 2 to the x equals 11 would have to be larger than 3 and smaller than 4. Do you agree with that? In other words, this scenario. Everybody see that? Okay, I'll assume that means yes. Through the trial and error process, I could take 2 to the 3.1, 2 to the 3.2, 2 to the 3, and just keep going and get approximately 11, however long I wanted to spend on it. Not a very efficient way of doing it. What we can do is we can take 2 to the x equals 11, and we can take this exponential equation and rewrite it as what's called the logarithmic equation. And I'm going to put a little arrow here. This would be log base 2 of 11 equals x. Now, unless you've been exposed to logarithms before, you're going, what just happened? What is log base 2 of 11? And we're going to talk about that. This next few sections, we're going to be dealing with logarithms. But the thing I want to point out at this particular moment is that writing it in this form isolates x. So if we could evaluate that expression, which we will ultimately learn to do, we could then determine what x is. So if we have an equation where the unknown is the exponent, we can solve it by converting that equation into a logarithmic equation. Now let's take a look at what I did there. 2 to the x power equals 11 is equivalent to log base 2 of 11 equals x. What I want to point out is this. In this first equation, 2 to the x equals 11, the 2 is the base, where the x is the exponent, okay? On the right side, log base 2 of 11 equals x, the way we say that, the 2 is also considered the base of that equation. So what I want to show here is that going from exponential to logarithmic form, or logarithmic form to exponential form, the base stays the same, okay? But the other two numbers change places. Let's see how that works. So let's say I've got log base 3 of 81 equals 4. I want to take this logarithmic equation and change it to exponential form. Log base 3 of 81 equals 4. 3 is the base. Well, in exponential form, it would be 3 to the 4th power equals 81. So the base stays the same, but the other two numbers change places. Any questions about this example? All right, let's take a look at another one. Log base 7 of 7 equals 1. In exponential form, this would be 7 to the 1 power equals 7. Or log base 10 of 100 equals 2. Log base 10 of 100 equals 2. This would become 10 to the 2 power, or 10 squared, equals 100. Again, any questions about changing from logarithmic form to exponential form? The base is the same, and the other two numbers change places. All right, how about this one? Log base 6 of 136 equals -2. 6 to the -2 power equals 1 over 36. Log base 8 of the cube root of 8 equals 1/3. 8 to the 1/3 power equals the cube root of 8. Isn't that true? A 3 as an index on a radical would be a 1/3 as an exponent in exponential form. Okay. Log of 0.01 equals -2. Well, we have a problem here in that there's no base written. So in the use of logarithms, there are a couple of numbers that appear a lot. One of them is base 10. Because base 10 is used quite frequently, we think of base 10, it's called common base. And mathematicians are always efficient. And so what they decided was that if we have a situation that's log base 10, we just will leave the base blank. We won't put anything there, and we'll just know that that's log base 10. So there's an implied 10 here. So this becomes 10 to the negative 2 power equals 0.01. All right. So again, log base 10 is written log. On your calculator, at least on my calculator and most people's calculators, there's a button that says log. If you look closely at that button, the second function key should be 10 to the x power, which is a way of reminding you that that button that says log means log base 10. Any questions about that? All right. X equals log base 9 of 81. So this would be 9 to the x power equals 81. Log base m of p equals 101. So m to the 101 power equals p. Again, any questions there? So this is converting logarithmic equations to exponential equations. Now we're going to go the other direction. We're going to take an exponential equation and convert it into logarithmic form, into a logarithmic equation. So 8 squared equals 64. 8 is the base. So log base 8 of 64 equals 2. 10 cubed equals 1,000. Log base 10 of 1,000 equals 3. This could also have been written log of 1,000 equals 3 because the 10 would be implied. Okay. 3 to the negative 4 power equals 1 over 81. Log base 3 of 1 over 81 equals negative 4. M to the n power equals p. Log base m of p equals n. 12 to the negative 2.6 power equals n plus 1. Log base 12 of the quantity n plus 1 equals negative 2.6. Notice I needed to quantify that because if I wrote it like this, that would imply we wanted the log base 12 of n and then just plus a particular, just plus 1. And we want that whole thing to be included. So we need to group it there. All right, now, changing back and forth between logarithmic equations to exponential equations, I can't talk, and exponential equations to logarithmic equations is a very important part of mathematics, especially in this chapter. I would say that when you're solving an equation that's an exponential form, most of the time to solve it, you're going to put it in logarithmic form, and vice versa. When you have an equation you're trying to solve that's in logarithmic form, most of the time you're going to convert it into exponential form in order to solve it. So this changing back and forth between the two forms is probably the most important idea in this chapter. All right. Now, we have the following equation. Log base x of 81 equals 2. So we want to solve this thing. Log base x of 81 equals 2. Writing this as an exponential equation, we get x squared equals 81. Okay. Well, let's see. X squared equals 81. We could solve that by a number of methods. We could set it equal to 0 and factor it. It's already in the form that you would use the square root property, or we could put it in standard form and use the quadratic formula. Well, since it's already in the form for the square root property, let's just go ahead and do this. So we get x equals plus or minus 9. So x equals negative 9, x equals 9. However, should we have a way to plug this in, we would discover that negative 9 is not a correct answer, that only the positive 9 is a correct answer. So let's figure out why that's true. Okay, let's go back to y equals b to the x power, okay? When we were starting to look at exponential equations, and we said that b had to be greater than 0 and b could not equal 1, right? Because if b was 0, or excuse me, if b was either 0 or negative, you don't get a graph that looks like an exponential. In fact, you can't even graph it, the first one, okay? And then if b was 1, you'd get a constant function. So we had those restrictions. And then we said what the domain, that is x, could be what? Anything from negative infinity to positive infinity. But the range was going to be greater than 0. Remember, if we graph this thing, it's going to look like that, or it's going to look like that. But so your domain is all real numbers, but your range is greater than or equals or greater than 0, but not equal to. Okay, do you remember all that? So now let's take this and let's change it into a logarithmic equation. Log base b of y equals x. Well, this b is the same as this b, so it has that restriction on it. Oh, so that means our base has to be greater than 0 and not equal to 1. Okay. Also, this x is equal to that x. So over here, the domain is all real numbers, which means our answer to a log can be any real number. It can be positive or negative or 0. And then let's see here. This, that doesn't show up very well. This is that. Y, the range has to be greater than 0, which means, oh, we have to take the log of something greater than 0. So if I have log base b of y equals x, b has to be greater than 0 and not equal to 1. Y has to be greater than 0, but our answer, or I should say the thing we take the log of, has to be greater than 0, and our answer can be any real number. All right, so with all that in mind, this cannot be negative. So the final answer is just x equals 9. And later, as we punch things into our calculator, we'll see that if we put in a number that isn't acceptable, the calculator will say something like error or domain error, and we'll deal with that when the time comes. All right, any questions about that? I know there was a lot packed into that one problem. Okay, how about this? Let's see. Log base 7 of x equals 0. Changing this into an exponential equation, we get 7 to the 0 power equals x. Well, what is anything other than 0 to the 0 power? It's 1, so x equals 1. Questions there? All right. Log base 4 of 16 equals x. So 4 to the x power equals 16. One of the ways we can solve an equation of this type is if we could take both sides of the equation and write them with the same base. For instance, 16 is 4 squared. And I'm not going to go into great detail here, but because logs and exponential equations are one-to-one functions, if we write them so that they have the same base, we can assume that the exponents are equal as well. And there are some fancy techniques that we will not be exploring this quarter. You'll probably learn them if you go on and take, what is it, Math 140, Math N 141. Anyway, so here we have x equals 2. So log base 4 of 16 equals 2. Questions about that example? Okay. How about this? Log base 3 of x equals -4. So 3 to the -4th power equals x, which is 1 over 3 to the 4th power, which is 1 over 81. So x equals 1 over 81. Let's see here. Log base x of 0.001 equals -3. Writing this in exponential form, x to the -3 power equals 0.001. Well, if we could write this equation so they had the same base, the exponents would be equal. Or if we wrote it so they had the same exponents, the bases would be equal. How could we do that? Well, 0.001 would be 1.0 times what? Let's see. 10 to the -3 power. Wouldn't that be 1, 2, 3? But isn't 1.0 times 10 to the -3 power just 10 to the -3 power? So I could write the equation x to the -3 equals 10 to the -3, therefore x equals what? 10. Okay, so here we made the, let's see, wait a second. Here we made the bases the same, so the exponents were equal. Here we made the exponents the same, so the bases were equal. Okay. Let's see here. Log base x of 100th equals -2. X to the -2 power equals 100th. X to the -2 power equals 1/10 squared, which is 10 to the -2 power. Therefore, x equals 10. Any questions there? Okay. How about this one? Log base x of 9/4 equals 2. X squared equals 9/4. How about x squared equals 3 squared over 2 squared? X squared equals 3 over 2, the quantity squared. Now, we're used to going perhaps that direction and then that direction, but here we want to get it in this form. So I can take that and go into that form. So now take the square root of both sides. Let's see here. Well, I don't even need to do that. Just I've got the same exponent, so x is 3/2. I could get there ultimately, and we'd throw out the negative because remember, again, the base can't be negative, as well as some other restrictions. Okay, now this says evaluate each logarithmic function, log base 3 of 9. So it's just an expression. Well, it has to be equal to some answer. How about if we just say it's equal to that box? So that means that log base 3 of 9 equals whatever goes in the box. Well, now I've created a logarithmic equation. I could convert that into an exponential equation. I could take 9 and write it as 3 squared. It's a sad looking box. So 3 to the box equals 3 squared. The box equals 2. All right. Let's say we've got this situation. Log of 100,000. Well, isn't that the same thing as log base 10 of 100,000? Remember, there's an implied 10 if there's nothing written there. We'll say that's equal to some box. So writing it as an exponential equation, 10 to the box equals 100,000. But isn't 100,000 10 to the, let's see, 1, 2, 3, 5th power? So the box would be 5. While we're at it, let's introduce the idea of the calculator. Now, I already pointed out and said that there was a button that said log that was log base 10. So let's do this problem on the calculator. So I'm going to push the log or the log button. And when I do, this appears on my calculator. I put in 100,000 and close it up and push equals, and I get 5. Try that if you've got your calculator handy. you should be able to get the 5 as an answer. Okay, let's do another one. This says log 1 over 10,000 equals. So log parentheses 1 divided by 10,000 close parentheses, 1 divided by 10,000, and I get -4. Let's do it the long way. Okay, so we're going to say that equals some box. There's an implied 10 here. So that means 10 to the box equals 1 over 10,000. 10 to the box equals 1 over 10 to the 4th. 10 to the box equals 10 to the -4. The box equals -4. Okay. Much quicker on the calculator, wasn't it? Yeah. Okay. Here it says, use a calculator to find each value. Give answers to 4 decimal places. So they want the log of 3.25. So basically that's log base 10. But on our calculator, the button just says log. So we push that, we get log parentheses 3.25. Close parentheses equals 0.511883361, but it said to 4 decimal places, so that's right here. The 8th and the 5th decimal place would round up, so we get that as our answer. Okay. Any questions there? Let's see here. Let's try the log of 375.876. So again, that's log base 10. So log, and then I put in 375.876. 375.876 equals 2.57504. It goes on from there, but it said 4 places. So here, that's the 4th place. The 4 would round down. So 2.5750 would be the answer. All right, let's try the log of -3. So log -3, close it up. -3, close it up equals, and I get domain error. Okay, we can't take the log of a negative number. That was one of the things we discussed back there ways. Okay, now this says use a calculator to solve each equation. Round answers to 4 decimal places. Log of x equals 3.7813. This is a logarithmic equation. It's log base 10. I'm going to write the 10 there, that's assumed. If we were to change this into exponential form, we'd have 10 to the 3.7813 power equals x. Well, 10 to the 3.7813 power equals. There are 2 ways, at least 2 ways, we can access this on our calculator. We can just put in the number 10. Okay, and then use the little power caret key. And then in this case, since we've got a single quantity that's the exponent, we don't need any more parentheses. We'll go 3.7813 equals. And I get 6043.659664. That's the 4th decimal place. The 6 rounds up. So 6,043.6597 should be the answer. Okay, now another way we can do this. Remember I said that the button above log was 10 to the x power. So this is the second function of this button. So I could start by going second and then push the log button, which then is getting to the 10 to the X button. And when I do that, this shows up. Then I'll put in the 3.7813, close it up, equals, and you get the same thing. So you could either do this or that. Okay, you should get the same answer either way. Okay, now let's take a look at a situation that says stocking lakes, as in filling them with fish. A farmer stocked a lake on her property with 75 sunfish. She was told that with the proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus 45 times the log of t plus 1, where t is the number of years since the lake was stocked. Find the number of sunfish she can expect in the lake in 2.5 years. So basically, what is f of 2.5? 75 plus 45 times the log of 2.5 plus 1, which is 75 plus 45 times the log of 3.5. So on the calculator, 75 plus 45 and then log of 3.5, close it up, equals, and I get 99.483062. So I suppose in this case, it would be appropriate to round off to the nearest sunfish, which would be 99. There's 0.48 of a sunfish swimming around there. Yeah, all right. Any questions about that? Take a look at another example. This says children's height. How tall is a child? The logarithmic function h of a equals 29 plus 48.8 times the log of a plus 1 gives the percent of the adult height a male child a years old has attained. If a boy is 9 years old, what percent of his adult height will he have reached? So h of 9 is 29 plus 48.8 log of 9 plus 1, which is 29 plus 48.8 log of 10. So on the calculator, 29 plus 48.8 log of 10, close it up, and I get 77.8. So that is what percent of adult height. So this is saying that on average, a male child that is 9 years old has reached 77.8% of their adult height. That doesn't mean that a specific child will do that, but on average, they must have checked a whole bunch of children. Okay. So what's coming up the rest of this week? Tomorrow, we're going to take a look at 11.5. Wednesday, we'll basically do 11.6 and 7 in the chapter review, which seems like a lot, but 11.6, we're only going to take one formula from it and apply that in 11.7. Thursday, we'll review. Friday, you'll have your last chapter test. And then going on into next week, Monday and Tuesday during this hour, we'll review for the final exam. That is due no later than 11:30 or 11:59 p.m. on Wednesday. Okay. Anyway, I'm going to go ahead and stop the recording.